The Vinci Xi surgical system is the fourth-generation robotic-assisted surgical platform and is designed to facilitate complex, minimally invasive procedures across a wide range of surgical domains, particularly where precision, dexterity, and multi-quadrant access are critical. Its primary applications include colorectal, urologic, gynecologic, thoracic, and general abdominal surgeries. In colorectal surgery, it is commonly used for procedures such as low anterior resections, total mesorectal excisions, and multi-quadrant colectomies, where fine dissection around neurovascular structures is required. In urology, the Xi has become a preferred platform for robot-assisted radical prostatectomy, partial nephrectomy, and cystectomy, owing to its superior visualization and wristed instrumentation, which enhance nerve-sparing techniques and reduce positive margin rates. Gynecologic applications include hysterectomy, myomectomy, and endometriosis excision, particularly in patients with extensive pelvic adhesions or deep infiltrating disease. In general surgery, the Xi is increasingly employed for ventral and inguinal hernia repairs, cholecystectomy, gastrectomy, and bariatric procedures such as sleeve gastrectomy and gastric bypass. The system's ability to access multiple quadrants without repositioning is especially valuable in complex oncologic surgeries requiring en-bloc resections or lymphadenectomy. Additionally, the Xi platform is expanding into thoracic applications, including lobectomy and mediastinal mass resection, where precise navigation around vital structures such as the heart and lungs is essential. Across these domains, the Xi is particularly beneficial in cases where conventional laparoscopy is limited by restricted instrument articulation, difficult anatomy, or the need for extensive intracorporeal suturing. At the core of the Xi's design is a boom-mounted overhead arm system that decouples instrument positioning from fixed bedside orientation. The boom provides 330 rotational freedom around the vertical axis of the patient, enabled by a gimbaled mount and a rotational bearing with multi-channel cabling for power and signal continuity. This reconfiguration supports true multi-quadrant access without the need to undock and redock the robotic arms, a limitation present in the Vinci Xi platform. Each robotic arm operates via a redundant 7-degree freedom DOF actuation system. 3. DOF at the proximal arm joints, shoulder-like yaw, pitch and roll. 3. DOF at the instrument shaft insertion, rotation pitch, and 1 DOF at the instrument tip wrist roll. The design employs harmonic drive reducers and brushless DC servo motors to deliver high torque with low backlash, ensuring micron-scale precision in tip articulation. The arms also feature collision avoidance algorithms and force-limiting protocols based on proximity sensors and torque feedback control loops. The master console is ergonomically configured with reflective haptic interfaces, stylus-like master manipulators that operate under a master-slave teleoperation model. Input motion from the surgeon is sampled at high frequency, approximately 1 kHz, filtered for tremor using a low-pass recursive filter, and scaled according to user-defined gain parameters, typically 3:1 to 10:1. The data is processed by a real-time control kernel executing inverse kinematics to map hand positions to instrument tip trajectories in 3D Cartesian space. End effector motion is governed by a combination of Denevitt-Hartenberg, parameter-based forward kinematics, and Jacobian-based inverse dynamics, optimized for smooth trajectory tracking and joint space constraint handling. The system can perform null space optimization to avoid joint limits and ensure cable tension balance in multi-DOF actuators. Tip articulation is facilitated by endorsed instruments, each featuring micro-servo-driven joints with an angular range of plus or minus 90 and roll motion exceeding 3,540, mimicking human wrist biomechanics. The Xi platform incorporates a fully digital 10mm 3D endoscope with dual image sensors, delivering high-definition stereoscopic output 1920, 1080 resolution per eye. The optics are relayed via fiber-coupled LED illumination and processed using stereoscopic image rectification to maintain depth accuracy under variable focal lengths. The system achieves 10 optical magnification with digital zoom augmentation for enhanced sub-millimeter visualization. Visualization data are streamed through a GPU-accelerated rendering engine, allowing for near-zero latency display at the console. Integrated near-infrared fluorescence nerve imaging is enabled via the Firefly system, providing real-time perfusion assessment with endothianine green ICG injection, aiding in vascular and oncologic margin visualization. Performance comparisons between robotic and conventional laparoscope platforms highlight several Xi-specific advantages. In a peer-reviewed research study, the Xi platform demonstrated a conversion to open rate of 5.4%, significantly lower than the 12.2% observed with conventional laparoscopy in colorectal procedures. Additionally, mean intraoperative blood loss was reduced by 75 milliliters p 0.01, attributed to finer dissection control and reduced tissue trauma via high-resolution endoscopy. Operative duration and workflow efficiency analyzed in ventral hernia repairs yielded a mean operative time of 185 minutes, compared to 205 minutes with the C system, largely due to reduced docking time and optimized quadrant access. These efficiency gains are attributable to improvements in automated port targeting, a laser-guided calibration routine that aligns robotic arms with trocars via spatial registration and pose estimation. Postoperative metrics also favor robotic-assisted approaches. Median hospital length of stay was 1.2 days for XI procedures versus 2.3 days for open surgery. A meta-analysis encompassing over 25,000 cases found that robotic surgery outcomes in urologic and colorectal domains were statistically superior in complication rates, CI 95%, and surgical margin negativity when adjusted for patient comorbidities and institutional learning curves. From a systems design perspective, the XI's footprint was reduced by 20% compared to prior generations through re-engineering of the patient cart chassis, incorporating cast aluminum alloy components and integrated cable routing. The overhead boom arm is modular, supporting multiple patient table configurations. The camera arm is now automated and auto-targeting, reducing human error and improving setup time consistency. The XI platform is integrated into hospital informatics via secure HL7 messaging for case documentation and supports procedural video capture, telemetry, and onboard analytics for instrument wear monitoring and usage tracking crucial for surgical quality assurance. Despite its acquisition costs, $2.2 million, and procedural cost estimates ranging from $1,800 to $3,000 per case, studies have begun to demonstrate potential economic offsets. Reduced complication rates, lower conversion rates, and shorter lengths of stay translate to reduced resource utilization and improved throughput. Health economic modeling suggests that under high-volume use cases greater than 250 cases a year, cost neutrality may be achieved within 3 to 5 years, particularly in high-complexity surgeries with significant morbidity reduction potential. The Da Vinci Xi surgical system exemplifies the fusion of advanced mechatronics, real-time control systems, and surgical workflow engineering. Its platform represents a scalable architecture capable of supporting future AI integration, real-time force feedback, and autonomous navigation systems, while economic and institutional adoption hurdles remain. The Xi system sets a high benchmark for precision, adaptability, and integration in robotic-assisted minimally invasive surgery.